So we'll start the class now. In the previous class, or in fact in the previous two classes, we have seen how we can compute stresses and deflections in a helical compression spring. So now, once you know that, after that we'll move on to the design of these helical springs. Once you are able to calculate the stresses and deflections in the spring, you can go for the design of an helical spring. If you recall that, so the stress in case of helical spring, which is subjected to either tension or compression force, or which is an axial load, we see that the stress is going to be a shear stress. Of course, there are three shear stresses are there. Those are torsional shear stress, direct shear stress, and shear stress due to curvature. So we included all these things just by applying the wall stress correction factor to the torsional shear stress. So that is how you can calculate the stresses in the spring. So after that, we have seen the deflection equations also. That is, what is the axial deflection of the spring? We derive an expression for the deflection of the spring also. Okay, now moving on to the design of helical spring. This I think already told to you well the beginning when we are taking up that calculation of the stresses in the spring. So there should be some objectives or the design is based on the three criteria. One is it should possess sufficient strength to withstand the external load. That means that type of design criteria what we will call it as based on strength criteria. This I already told to you. So therefore, whenever you have a strength criteria, you need to determine what are the stresses in the spring, and then you need to compare whether the individual stress is less than the allowable stress or not. So if it is satisfied, then we can say the stress is the spring is or the design is safe. Then the second criteria is it should have the required load deflection characteristics. That is nothing but a stiffness criteria. So it should have the required load deflection characteristics, and third one is it should not buckle under the external load. This is the third, especially for case of springs we'll use this criteria. Otherwise, generally we'll use for only those two criteria, that is strength and stiffness criteria only. But in case of spring, we'll go for the third one also, whether it is stable under the given external load or not. That means it should not buckle. So now I think these things we already we discussed all those things. So then generally if you talk about the design of a spring means what you need to determine or what are the parameters which are important in the design of the spring. So generally it is possible to design a number of springs for a given application by changing only three basic parameters. So that means if you take any helical spring, its design is based on changing three parameters. So for a same application, I can design different types of springs. Different types in the sense, spring is going to be helical spring only, but only thing is by changing the three different parameters, I can have different designs for the same application. What are those three parameters? One is wire diameter, then mean coil diameter, and then number of active turns. So that means in design of helical springs, these three parameters will play a vital role. That means the important thing is you need to design only these three parameters for a spring. So then the rest of the parameters are derived from these parameters only. So once you have wire diameter, mean coil diameter, and number of active turns, then remaining parameters, whatever you want, that is solid length, free length, or maybe the number of inactive coils, all those things will be derived from these three parameters only. So that means, suppose if anybody is talking about the design of the spring means determination of these three parameters: wire diameter, coil diameter, mean coil diameter, and number of active turns. Wire diameter will use small d for wire diameter. Mean coil diameter will take it as capital D, and number of active turns will take it as n. And also we know that there is a relation between these two also, wire diameter and mean coil diameter. The ratio of mean coil diameter to the wire diameter we call it as spring index C. So that means either out of these three, wire diameter, mean coil diameter or spring index, So you can say in other words, out of these three, you should know two values. That is wire diameter, spring index, then number of active turns. So in that way also you can say that those are the three basic parameters one has to identify in design of any helical spring. So however, there are practical limitations on these parameters. So what are those practical limitations? In certain applications, there are some space limitations. The spring is to fit in a hole of certain diameter where the outside coil diameter is restricted. So that means, so even though we are playing with these three parameters, that is wire diameter, mean coil diameter, and number of active turns, there are some practical limitations. What are those practical limitations? Those practical limitations will arise from the application where you are using the particular spring. Suppose, like here it said, so I want to use a spring in an application where I need to insert the spring into a hole. So there the old diameter is fixed. So there in that application I need to insert the spring in a hole. That is my application. So in that application, so now since you need to require insert the spring into the hole, you cannot take the outer diameter of the spring is more than the hole diameter. Outside diameter of the spring should not be more than the hole diameter. So then if it is more, you cannot insert the spring into that application. So that means you cannot use that particular spring in the given application where you want to insert the spring into a hole. So therefore the restriction is I cannot choose the mean coil diameter like any value here because there is a restriction on outside coil diameter. There is a restriction on outside coil diameter because of you are using that in an application where you want to insert the spring into a hole of having certain diameter. So that means a restriction on outside diameter is nothing but restriction on mean coil diameter also. Because your mean coil diameter is d0 plus dA by 2. So the dA is restrict dA, so that means you cannot take any dA value or dO value. So restriction is there, and dO means restriction is there on the mean coil diameter also. So if restriction is there on mean coil diameter, then so we have a for practical applications we have a spring index which is ranging from 6 to 12. In all practical applications, when the load is a static load, there is a restriction on spring index. You cannot take any spring index value. You have to take only between 6 to 12. So if I fix that, so based on that, your wire diameter will also depends. So that's why there are some limitations. Even though you cannot choose all this wire diameter, mean coil diameter, number of active turns as per our wish. So there should be some limitations or restrictions on these diameters also based on the given application. So here this is the application where you have a limitation or restriction on the outside diameter. Sometimes the other way is also true. That means there are, suppose if I want to here, I am saying that I am using a spring which is need to be inserted into a hole. So then there is a restriction on the outside diameter. Whereas if I take it the other way, so that means instead of a hole, if I want to insert the spring into a rod, like you will take your ballpoint pen. So in all ballpoint pen earlier, there is a springs are there in that. So what is that? The refill is inserted into the spring. A refill is inserted into the spring. So that means here, so whatever may be the diameter of the refill, so the inside diameter of the spring should not be less than the diameter of this refill. Then if that is the case, you cannot insert the spring into the refill, you cannot insert the refill into the spring. If the inside diameter of the spring is less than the diameter of the refill, so then you cannot insert. Or else, in other words, diameter of the refill is more than inside diameter of the spring. No, that's it. You cannot insert the refill into the spring. So that means the inside there is a restriction on inside diameter of the spring also. That means where you have certain application where if you want to insert the spring to a rod, rod is nothing but here in our example it is a refill. So refill is nothing but a kind of a rod. So then in that application you have a restriction on inside diameter. If you are in your application, the requirement is if you want to insert a spring into a hole, then there is a restriction on outside diameter, or in some other application where I want to insert the spring to a rod, then there is a restriction on inside diameter. So that is what I written here. In some application, a spring is to be fit over a rod where minimum inside diameter of the coil is specified. Before proceeding to the design calculations, the designer should specify the limits on the diameters. So therefore, see here, while we are saying that only these are the three parameters, basic parameters we need to determine for a design of helical spring. So not only that, so depending upon the application, you need to specify that what are the limits for these dimensions also. That is, what is the limit for mean coil diameter also. So then only that limitations will arise from the given applications. Like what we discussed here, in one case you have a restriction on DO, in another case you have a restriction on DI. So that depends upon the application. Sometimes there is no restriction, you can take anything, any diameter. So like that. So that depends upon purely on the given application only. Okay, so then the main dimensions to be calculated in the spring design are wire diameter, coil diameter, and number of active coils. That's what we already discussed. So these are the three main diameters we need to calculate. The first two are calculated by the load stress equations, while the third is calculated by the load deflection equation. So that means here, so in design of helical spring, you need to calculate or you need to determine the three important parameters. Those are wire diameter, mean coil diameter, and number of active turns. So then in this, the first two, that is mean wire diameter and mean coil diameter, is calculated based on load stress equation, means load based on the shear stress equation, resultant shear stress equation, what we discussed earlier. That is, resultant shear stress tau is equal to what you get is some K. K is nothing but your wall stress correction factor, K multiplied by 8 into PD by pi d power 3. So that is what we got it is. That is torsional shear stress multiplied by wall stress factor. So in that equation, if you know the load and if you know the allowable shear stress, then you can calculate what is the wire diameter. Provided if you know the relation between mean coil diameter and wire diameter. So therefore you get those two relations. Once you have done that, then the third one is calculated by the load deflection equation, means we derived an expression for delta. We derived the expression from delta. From that, in the delta equation, if I go back to that equation, yes, here. So this is the equation where we'll use to determine either this d, small d, or capital D. This is what we call it as stress equation. Then, if I go for the delta equation here, you can see that here delta is nothing but 8 PD cube n by GD power 4, where this n is nothing but your number of active coils. So once you if you use the load stress equations, you already know all these diameters, D, capital D, small d, everything is known. Only unknown is n. So from the delta equation, you can calculate the number of active coils also. So that's what I stated here. The first two are calculated by the load stress equation, while the third is calculated by the load deflection equation. Then comes factor of safety. So here, like I already told here, in load stress equations, what we are saying that you need to calculate you need to determine the design equation. Design equation is nothing but what I am saying is that if individual shear stress is less than the allowable shear stress, then we are saying that the design is safe. Then what is that allowable shear stress? I will calculate. That allowable shear stress is calculated based on that shear strength of the spring. So since if I take the shear strength is some SYS, so that we get from that yield strength. Then what we'll do is we'll apply some factor of safety to do that shear strength, so that you will get your allowable shear stress. So that why we are considering factor of safety also here also again, because we are not sure whether the material of the spring is uniform or not. So like that, so many factors are there. Generally, we'll use factor of safety in all the designs, so to avoid unforeseen factors. So therefore, that's why it is called factor of safety. So in case of the springs, always the factor of safety is taken as very less. So here, generally in all other applications, if you look at the factor of safety is some 4, above 4 it will be, whereas in case of the spring design, the factor of safety is going to be around 1.5 only. So why only it is 1.5? The reasons were also listed here. We can go through those things here. The factor of safety in the design of spring is usually 1.5 or even less than 1.5. The use of relatively low factor of safety is justified on the following grounds. So why we are using very less factor of safety in case of the spring design is because in most of the applications the springs operated with well-defined deflections. Like already told, we'll use this factor of safety to counter or to accommodate unforeseen effects. So here in case of the springs, here that uncertainties are very less. Uncertainties are very less. So that's why we'll use less factor of safety or low factor of safety. In most applications, see in that way we can say the uncertainties are less. The springs are operated with well-defined deflections. That means you have a prior knowledge. So what are the deflections of the spring? So that means there is no uncertainty. Therefore, the forces acting on the spring and the corresponding stress can be precisely calculated. So that's why your factor of safety is low in case of the spring. So you can precisely calculate the stresses which are going to induce in the spring for a given load. So therefore, the necessity of factor of safety will be reduced. So it is not necessary to take higher factor of safety to account for uncertainty in external forces acting on the spring. So that means generally we'll take the factor of safety to overcome the uncertainties. So suppose if I am unable to estimate what is the magnitude of the load acting on the spring exactly or precisely, if I am, see, we know that the stress is induced because of the P. If you look at the equation for the stress, tau is equal to K into P dq by P into dy 8 into P d by pi d cube. So in that you have a load P is there. If I know exactly this is going to be the P value which is going to act on the spring, then no need of considering the factor of safety. If I have some uncertainty in determination of the magnitude of P precisely, then we need to go for the higher factor of safety. So here in most of the spring applications, the load which comes onto the spring is going to be determined more precisely. So that's why a low factor of safety can be used in case of the spring applications. Not only that, in case of helical compression springs, an overload will simply close up the gaps between the coils without a dangerous increase in the deflection and stresses. So that means even if you are not calculating the load precisely, so that means you estimated the load as a 100 newtons on the spring, but if it exceed further, so that means if it is exceed 100 newtons, let us say if the actual load coming onto the spring is 110 newtons, so then we'll say our estimation is underestimation. Actual load is 110 newtons, but we are estimated as a 100 newtons only, means we underestimate the load. So that means the load is overload now for the spring design. For the spring, what we designed it for 100 newtons load, but now the load acting on the spring is actually it is 110 newtons, means it is overloaded. So then if it is overloaded also, then there is no danger. So why? Because here there is a gap between the coils, adjacent coils in the spring. So now if load increases further, then what happens is the gap between those coils may be decreased and they come in contact with each other. So therefore this certain amount of overload. So I can't say that you can go for any amount of overload. Only a certain amount, a small overload cannot cause any dangerous deflections and stresses in case of the springs. So that is the another reason why we are going to use a low factor of safety in case of these helical springs. Then third one is in case of helical extension springs, usually overload stops are provided to prevent excessive deflections and stresses. That means this is some sort of mechanism where you can avoid overloading of this tension springs or extension springs. So there are some mechanical stuffs which can be provided to restrict the overloading of the spring. So therefore, there also that means you are restricting the overloading the spring means your load acting on the spring is going to be as per our calculation. So that means it is not going to be much overloaded. So therefore, whatever equations you calculated for the stress, whatever equations you are going to use to calculate the stress values, they are close to the actual values. So therefore, the need of higher factor of safety is not considered. Only the factor of safety is taken as low, which is close to 1.5 or even less than 1.5. Then the spring material is carefully controlled at all stages of manufacturing. The thin and uniform wire cross section permits uniform heat treatment and cold working of the entire spring. So, if you talk about the material homogeneity, like already at the beginning I said it. So, generally we consider the factor of safety for uncertainties. Uncertainty may be in the determination of the load, maybe uncertainty in the homogeneity of the material. So first case we already discussed, that is the load, the uncertainty in calculation or in determination of exact load, what is going to act on the spring is going to be less in case of the springs. That is the one reason why we are using the low factor of safety. Even in the material point of view also, the springs are manufactured carefully in a controlled manner at all stages of manufacturing. So and also it is heat treated uniformly, and that means while manufacturing the spring, a lot of carefulness will be used so that the uniform, there is a uniformity in the material for the entire spring. That means the uncertainties in the material composition will also be very less in case of the springs. So therefore, you don't require very high factor of safety. So therefore, the factor of safety based on torsional yield strength. So since we are using the torsional shear stress as a design criteria for the springs, so you need to consider what is the torsional yield strength, which is known as SYS or SY. Simply S capital X is for the strength, SY is for yield strength in shear. SY indicates that it is yield strength in shear. Is taken as 1.5 for the springs that are subjected to static forces. When a spring is subjected to a static force, the factor of safety is considered as 1.5. Or not only that, maybe sometimes even less than that also, people will take that based on the given applications. Okay, so generally we'll take that this is the allowable stress. So now I will calculate the allowable stress. Your allowable stress is nothing but tau. Tau is the allowable stress, allowable shear stress, which is nothing but here shear strength of the spring material divided by factor of safety. Factor of safety is 1.5. So now using this calculation, you can calculate the tau. Once you have a tau, then you can equate this one to the your resultant shear stress. From that, you will get your wire diameter or maybe the mean coil diameter. So once you got that, so the first two parameters are evaluated. So then next one is by using the deflection equations. Okay, here. Okay. So using deflection equations, you can determine what are the number of active coils also. So there you don't need to use any factor of safety because while calculating the deflection itself, you know all the parameters, no need to use factor of safety there. Okay, right. So now once you understand these concepts, so once you know how to find out the allowable shear stress also, then we'll go for the design procedure. So this is the basic design procedure for a helical spring which is subjected to axial load. That means it may be a tension force or helical compression spring which is subjected to compressive load, or helical tension spring which is subjected to a tensile load. So for both compression spring as well as a tension spring, it is going to be same. The design procedure is same. Basically in design of helical spring, like what we discussed earlier, you need to determine only three parameters, that is wire diameter, then mean coil diameter, then number of active coils. So based on these three, you need to calculate what are the remaining parameters for the spring. Okay, so now we'll see the step-by-step procedure how we can design a helical spring. So first point in that is for the given application, estimate the maximum spring force, that is P, and corresponding required deflection. Here it is delta not D. Maybe it is a typing error. Delta is going to be the deflection of the spring. In some cases, maximum spring force and stiffness, which is are specified. That means, so first before going for the design of the spring, what you need to determine is we need to identify what is the maximum force acting on the spring, and then what is the maximum deflection in the spring. So P and delta are the requirement for the design of the spring. So sometimes instead of P and delta, they may take P and K also. So that is load and stiffness. Stiffness is nothing but P by delta only. So that's why indirectly we are taking the delta value only. So that means what you need to do is, so you have to use either P delta, or you need to determine P delta or P and K. So you have to use P delta or P and K. So that means the first step is you need to identify what is the requirements in terms of what is the maximum load acting on the spring. That is what we call it as spring force also. Then what is its corresponding deflection delta or maximum spring force or stiffness. Either you need to specify these are the two important parameters. Based on these two parameters only we are going to design the spring. Then that is the first step. In the first step, we'll identify what is P, what is delta, or what is P and what is K. What are the requirements for the spring? Then in the second stage, we'll select the suitable spring material. So once you select the suitable spring material, from that we can find out what is the allowable shear stress for the material. So that means select a suitable spring material and find out ultimate tensile strength from the data. So that means once you select the material for the spring, using your data book or from the literature, you need to find out what is the, in the data book you won't get the torsal shear strength. You don't get the shear strength in case of data book. In case of material properties, if you refer any data book, you will get only ultimate strength or yield strength. All these properties only will get. So those are the properties which are determined based on your tension test or simple tension test. So those properties are there in your data book. So you won't get a shear strength, all those things. So but once you have a ultimate tensile strength SUT, then using some our failure theory, static failure theories, we are able to find out what is the allowable shear stress. So here the permissible shear stress for a spring wire is taken as 0.3 times SUT or 0.5 times SUT. For the spring materials, generally, if you use your maximum shear stress theory, your SYS is nothing but 0.5 times SOID. So in the same procedure here, since here the spring material is not, it is a something like a mild steel. Here it is a some steel material, some patent steel or cold drawn steel, which is undergone some kind of heat treatment also. It is undergone some type of heat treatment also. That's why straight away I cannot take those values. But here the relationship for calculating the allowable shear stress is taken as 0.3 times SUT. So that is 0.3 times SUT is nothing but 0.3 into SUT is equal to your SYS. So whatever we written in this equation here, S into SY. This SY we are taking it as 0.3 times SUT. So now still we need to apply the factor of safety to that. If you take factor of safety 1, no need to apply that. So but here, because if you want to consider the factor of safety, to estimate this tau, you need to apply the factor of safety also. But here in this equations, it directly has taken tau is equal to 0.3 SUT or 0.5 SUT. That depends upon the materials. Either you can go for 0.3 SUT or 0.5 SUT. Then once you determine that allowable shear stress, then what you have to do is you need to assume the suitable value for the spring index. Like I already said, in case of static loading, you can take the spring index between 6 to 12. In case of dynamic loading, it is a somewhat restricted 8 to 10 in that range only. So therefore, most probably for all industrial applications, the spring index varies from 8 to 10. So that means you need to pick the spring index as between these two values 8 to 10. The spring index 8 is considered as a good value. So generally, if it doesn't specify anything in the problem, you take it as spring index as a 8. Okay, spring index will be taken as 8. Then once you have a spring index value, based on that you can calculate whatever you require, small d or capital D. The spring index for spring involves and clutches is 5. So there, in case of valves and clutches, they are subjected to fluctuating loads. If you take any valve or clutch, they are subjected to fluctuating loads. In that case, the spring index is taken as 5. But spring index should never be less than 3. This is we already discussed. You cannot take the spring index which is less than 3. Always it is in between practical application 6 to 12, like I already said. In case of the valves, it can be taken as 5. But in any case, it should not be less than 3. So that means first we identify what is P value and what is the D value, delta value. These are the requirements, design requirements. Then second step what we'll do is we'll select the material. So based on that material, we'll try to identify what is the allowable shear stress in that material. Then after that, we'll fix the spring index. Once we fix the spring index, then I can calculate wire diameter using this. Okay, so then what I do is first after that I'll use this. I'll calculate this. Once the spring index is fixed, I can determine this wall stress correction factor. Then after that, I'll find out the diameter, wire diameter using this relation. So here I know this tau, that is allowable stresses. I estimated in the second step. Then in this equation, if I want, I can convert this equation into in terms of C also here. So I know the K value here because I already fixed the C value. Spring index is fixed in the third step. So once I fix the C value, then I can calculate K value using this relation. I can take that K and I'll substitute here. In this, I know this tau, I know K. This D is there. This D I can write it as in terms of spring index also. We know that our C is equal to capital D by small d. So that means this is replaced by C into small d. I can write capital D as C into small d. So then it can be reduced further here. So therefore I can write the expression for tau as K into 8 P C divided by 5d square. So now in this equation I know tau. I already calculated the K here. Then I already know the P value. I estimated in the first step itself. I estimated the required load P. Then C is fixed in the previous third step. Then in this only unknown is D. So now if I solve this equation, I get the wire diameter. So once I get the wire diameter, then I can calculate this mean coil diameter also. That is capital D. Capital D is nothing but your C into D only. Once you fix the wire diameter, then this mean coil diameter is also fixed. So therefore, that is the next step. Determine mean coil diameter by the relationship D is equal to C into D. Then the next step is you need to calculate what is the active number of coils. So then you design primary parameters, that is small d, capital D, and N is going to be over. So we identified the small d and capital D here. In step 5, we identified the small d value. In step 6, we identify the capital D value. Next, we need to identify what is this N. So N is identified based on the allowable deflection or maximum deflection. Delta is equal to 8 PD cube N by 3D power 4. So this delta is identified or estimated in the first step itself. Like I already told, the requirements your requirement is what is the maximum P and what is delta. They are specified in the first stage itself. So this is known in this entire expression except N, everything is known. So now by solving this equation, I can find out what are the number of active coils also. N is determined here, where this N is nothing but number of active coils. Once I derived a design, once I estimated the number of active coils, then I will go for different styles, end styles. So then I'll choose as per my requirement. I'll choose a particular end style. Based on that, I'll calculate what are the total number of coils. So that is the next step. So in each step, you need to decide the style of the ends for the spring depending upon the configuration of the application and determine the number of active coils. Adding active and inactive coils, find out the total number of coils. So total number of coils is nothing but sum of active coils and inactive coils. So these inactive coils we already know. So depending upon the style of your ends. So we already discussed that is plane ends, grounded ends, and the square ends, plane and ground ends, and you have square and grounded ends. So for all those things we discussed what are the number of inactive coils in all those things. So that once you have number of inactive coils, then you can sum up inactive and active, you will get the total number of coils. That is step number 8. Then once you got that, then you need to determine what are the parameters of the spring. That is solid length, then compression length, then free length. Why we need to require free length? So to define the pitch of the coil, we need to calculate free length. So therefore, to get the free length, what we need to do is first we need to calculate what is the solid length. Solid length, we know the definition for the solid length. We already discussed that. Solid length is given by now total number of coils into D, where NT is sum of active coils for inactive coils. Then you can calculate the what is the actual deflection. See here, this actual deflection is different from what you estimated in the first step. This delta here, why it is different? Because see here I am using this equation. Using this equation, we are calculating the n value. So let us say by solving this one, I'll get n is equal to something like 8.9 or something I'll get. So I cannot have 8.9 coils. So now I'll round this n value to some 9. Next higher integer, I need to round it off to the next higher integer. That is n is equal to, from the calculation I'll get n is equal to 8.9, but I'll round it off to the next integer. So therefore it is going to be 9. So that means with this equation, if n is equal to 8.9 only, I'll get the delta what I estimated in the first step. But now from the after getting the calculation for n, I am modifying it by rounding it off. Now if I take n is equal to 9, now your deflection is not going to be the same as what you estimated in the first step. So it is going to change because if I substitute n is equal to 8.9, then I will get the delta value what originally I have taken. But instead of 8.9, I am taking n is equal to 9 means, so this delta is going to change slightly, not there is a large deviation in the delta value, but it is going to vary slightly. So that slight variation I need to use in calculation of the free length. So that's why we need to determine the axial deflection of the spring. Axial deflection means now we design we are taking the design parameters, that is D, capital D, small d and n. So then based on those parameters only you need to calculate the deflection here. So then that deflection we'll call it as an actual deflection. So here the formula is remains same, only thing is here you get your number of active coils here which are rounded value here, which is a rounded value here. Then after that we need to use to get that clash alliance. So sometimes people may take a gap of 0.5 to 2 mm between the adjacent coils when the spring is under the action of maximum load. The total gap, then the total axial gap is given by, so based on the gap you consider into number of coils, that is nt minus 1 only. So therefore your total gap is nt minus 1 into gap between two adjacent coils. Or sometimes this one is taken as this nt, instead of taking this nt minus 1 into this gap between the adjacent coils is taken as, here you measured as 0.5 to 2, or sometimes this gap between adjacent coils will take it as 15% of this maximum deflection also, 0.15 times delta also. They will take this one as this entire thing, that is 15% of delta, 15% of the maximum deflection, they will take it as the total gap. Like that also they may take it. So that depends upon the application only. So sometimes they will consider a 1 mm gap between the adjacent coils. So then the total gap is going to be your number of active total number of coils minus 1 into the gap. If I take this one as 1 mm, I need to multiply this one by 1. If I take 0.5 mm, I need to multiply by 0.5. Or some other value between 0.5 to 2, I have to take that value and I need to multiply this. So then we'll get the total gap. So then I know the solid length, I know the total gap, and I know the delta here. Using these three parameters, I can calculate the free length of the spring. So that's why here he said that in some cases the total axial gap is taken as 15% of the maximum deflection. That's what I already told to you. That is 15% means 0.15 delta. So then once you know all these things, you can calculate the free length of the spring is nothing but solid length plus this total gap plus delta. Here this is delta, this is delta. You know solid length, you know the delta, you know the total gap, then you get the free length of the spring. Once you have a free length of the spring, then in the next step you can determine what is the pitch of the coil. So then the pitch of the coil is determined by this relation. This we already seen, pitch divided by nt minus 1, where nt is the total number of coils minus 1. So like this we'll get the pitch of the coil also. So that means, so now the design is over. So finally, once you calculated all these things, you can determine the spring rate or spring stiffness is nothing but P by delta, which is given as d power 4 by 8 d cube n. So this is going to be the final parameter in your design. So like this, in these 14 steps, you need to design your helical spring. But in all these steps, the only major thing what you need to do is, you need to calculate what is small d, what is capital D, what is n. Remaining things are only, you need to use the formulas. All these formulas, everything is available in your data book. Only thing is, you should know out in the sequence how we can use all those formulas to determine various dimensions of the spring. So in that, first you need to identify whether small d or capital D. Then you need to calculate n. Once you have done that, then remaining things is using those parameters only you can derive all these parameters. So here we talked about the design based on. So if you look at this entire design procedure, it is based on only first one is strength. Then we use the stress equations, we use the deflection equations. But nowhere we are not concerned about the buckling. So, but in the beginning we said that there are three criteria. So we are not at consider the buckling here. So generally we'll follow some rules to avoid buckling in the spring. So that is, what are those thumb rules here? He said you can see in these two statements, you can see that a helical compression spring that is too long compared to the mean coil diameter acts as a flexible column and may buckle at a comparatively low axial force. So the spring should be preferably designed as a buckle proof. So that means if your spring design is such that its length is too long, if length is too long when compared to the mean coil diameter, that means the ratio of free length of the spring to the mean coil diameter, that is free length divided by mean coil diameter. So this parameter will decide whether your spring is going to buckle or not. So I think you know column buckling, you might have studied about column buckling there. So when the column is long column, then there is a buckling load is going to be very less. Well, in case of a short column, the buckling load is going to be very high. Similarly here, when the length is long column is, if the free length is more, so then it is more prone to the buckling. So therefore, you need to design the spring for buckling also. But if this ratio FL by D is less than certain value, no need to design the spring for the buckling. So that's what is written here. So compression springs which cannot be designed buckling proof or buckle proof must be guided in a sleeve. So that means if you are not designing the spring for a buckling, so then to make it buckle proof, so a sleeve or a guide is supported, the spring is supported through a sleeve. So that means it can resist the buckling. So then the spring will become a buckle proof. So now for that we need to use the following thumb rule. So what is the thumb rule? free length by mean coil diameter is less than 2.6 or less than or equal to 2.6. If free length divided by mean coil length is less than 2.6, then your guide is not necessary. That means the spring is not going to buckle for this condition. If free length divided by mean coil diameter is less than 2.6, so the spring is buckle proof already, so no need to design anything for the buckling. So that's why we are not discussing about the buckling. Then if when the free length divided by the mean coil diameter is more than 2.6, or when the ratio of free length to mean coil diameter is greater than 2.6, then a guide is provided so that buckling can be avoided. So that means in the spring design procedure we don't bother about the buckling. So only thing is we look at it into this ratio, that is when the ratio of free length to mean coil diameter is less than 2.6, there is no need of considering buckling failure criteria, so it is not going to buckle. When the ratio is more than 2.6, to avoid the buckling, a guide is provided for the spring. So guide is the form of a sliding rod. So it is provided so that buckling can be avoided. However, provision of guide results in friction between the spring and the guide, and this may damage the spring in the long run. So that means if it is buckling prone, if the spring is buckling prone, so now if you are not designing for the buckling, then you are providing a guide. So then the spring is having a sliding motion against this guide, which will cause a wear and tear in the spring. So that means this wear and tear will reduce the strength as well as the life of the spring. It will reduce the strength and life of the spring. That's what he said. This may damage the spring in the long run, in the sense when the spring is deflecting against this guide, so there is a sliding motion against the guide. So that means whenever there is sliding, friction will be there. So because of the spring friction, the spring will worn out. So that means there is a wear and tear in the spring, so which will reduce the load carrying capacity. Not only the load carrying capacity of the spring, it will reduce the life of the spring also. Okay, so that's why when it is designed with a guide, one has to take care of this effect also. Okay, so this is how basically we can design the spring. So this is the procedure we need to follow when we are going to design a helical spring. It doesn't matter whether it is a compression spring or tension spring, the design procedure is remains same. Okay, right. So with that, we come to the end of the theoretical discussion on the design procedure of this helical compression springs or helical tension springs. Now we'll take up some problems on the springs. How you are going to design the springs. So now for that, just you note down this problem. Anyway, we have 10 more minutes time. So I think we can I will explain the procedure, and then on your own you can do this also, because everything is available in the data book. All our things are available. You can easily do this also. So just note down this problem. I'll give you some time, 5 minutes. Then we'll go to the maybe in the next class we'll discuss about that one. So note down this problem. So before going to the note it down, so if you have any doubt in the so far whatever we have a discussion, if you have any doubt, then you can ask your doubt also. Otherwise, just note down this problem and then you can leave the class. For today, we'll stop this at this point. We'll discuss the solution in the next class. Just note down this particular problem and then you can leave the class. If you have any doubt, then you can ask your doubts also. Anyway, so we have 10 minutes time now. Why we need to waste the 10 minutes time? Anyway, note down that. So we'll discuss some a little bit, then we'll continue in the next class. So okay, first try to note it down. I'll give 2 to 3 minutes time, then we'll discuss the solution also. I'll read the problem. It is required to design a helical compression spring subjected to a maximum force of 1250 newtons. The deflection of the spring corresponding to the maximum force should be approximately 30 mm. The spring index can be taken as 6. The spring is made of patented and cold drawn steel wire. The ultimate tensile strength and modulus of rigidity of the spring material are 1090 and 81,370 Newton per mm square respectively. The permissible shear stress for the spring wire should be taken as 50% of the ultimate tensile strength. Design the spring and calculate 1. Wire diameter, 2. Mean coil diameter, 3. Number of active coils, 4. Total number of coils, 5. Free length of the spring, and 6. Pitch of the coil. Draw a neat sketch of the spring showing various dimensions. That is the problem. Just note it down, then we will discuss the solution. Okay, so if you note it down, uh, okay, so we'll close the class now. It is already 11:28. I'll close the class. So we'll discuss this in the coming classes. So just you respond to the admin sheet in the classroom and then you can give the class.